So that's okay with everybody. So let me kind of review the load equivalent secant theorem and show how it applies. So. Maybe I'll do a couple of examples. A couple of examples to illustrate how you always see the closed string fields when you do these computations. So what they should consider is the following. So suppose that A is an associative graded algebra and consider A tensored with GLN. This is a Lie algebra. Then we can take again a graded Lie algebra. There might be Z mod 2 graded, so there'll be signs in the commutators. We can consider the cochains of A tensor GLN. This is a cochain complex. So it's a DG commutative algebra. So why you might be interested in this is that in practice, anytime you have any GLN gauge theory, its algebra of local operators looks like this, with sum A. Local operators and gauge theory are of this form. So the first thing they do, it kind of looks like it's just some, some change of terminology. So it doesn't look like it does very much, but it actually is very useful. So we define cyclic cochains CCN of A is a collection of graded, cyclically symmetric, or antisymmetric, depending on the value of n, maps A tensor n to C. So it's like a multilinear map which takes n elements of A and gives you a number. And there's a differential as follows. If I have some phi A tensor n to C, then d phi of A1 d phi applied to n plus 1 inputs, phi A1, A2, A3, AN plus 1, minus plus phi A1, A2, A3, and so on. So we do the sum of all ways of contracting adjacent pairs, and this ends with the last one. I've taken the AN guy and brought it around to the front. So cyclic cohomology is the cohomology of this cochain complex, and it was introduced by Kahn. H star is the cohomology of the cyclic cochain complex. It's differential. Okay. So we're going to see how to compute this in a minute. So the theorem is that the limit as n goes to infinity of the cohomology, the algebra cohomology of GLN through A, is isomorphic to the symmetric algebra on the cyclic cohomology of A, with a certain shift in degree, which is not so important. This is the Lloyd equivalent secant theorem. It's actually extremely easy. So why is that? It takes well, this guy, GLN tensor A, has the same cohomology as the GLN invariance. So if we're thinking of this as like some model of local operators in the gauge theory, of course only GLN invariant things will contribute to the cohomology, but this is some general fact about Lie algebra cohomology. So for n really, really big, every GLN invariant tensor can be written as a product of any element here is a product of the functionals which send how to say it. Where there's AI are in A, MI are in GLN. So we're going to take, I want to build an anti-symmetric function of these guys, because that's going to be in the Lie algebra cochain. So I send that to the anti-symmetrization of phi A1 AN times trace M1 MN. Phi is a cyclic cochain. Okay. So phi is something which takes n elements of A and gives you a number that's cyclically invariant. And then I'm going to pair that with just the trace on these matrices. Now, we're going to anti-symmetrize, but because trace is the only, for n really big, capital N really big, the only symmetries this tensor has is cyclic symmetry. We're not going to lose any information about this. We're not going to project this onto a symmetrized part. Right? So this operation, like, it's saying it very well. So if we look at an anti-symmetric function on GLN tensor A and some power of that, when the rank of my matrices is really big, any such can be written as a product of single trace functionals, and the single trace functionals are all of this form. And then there's a little computation that the Lie algebra cohomology differential is equal to the cyclic differential. If we're going to think of this in more physical terms, you might think, suppose I have some gauge theory, GLN gauge theory for n really large. You want to write down the single trace local operators. those can always be written as just cyclic tensors in some fundamental space of fields, which is then tensored with GLN. So it can always be written as cyclic tensors like this. And the BRST differential is related to adjacent tensors contracting. Okay. So I know not everybody has like a homological algebra background. So I didn't want to go too much detail last time, but maybe it's good to do it more carefully.
How the BRST operator acts on that a single choice operator?
Yeah, so it's by this formula. So the fields are like some algebra tensor GLN. So the BRST operator just involves multiplication in that algebra. So I take a function of n elements. Sorry, take phi is a function of n elements of my algebra. D phi is a function of n plus 1. And d phi, like d is the BRST operator, is defined by this formula. I sum over ways of contracting the inputs, the adjacent inputs. Although in some examples, it might be an internal BRST differential on A, which will add on some additional terms. Okay, any other questions?
Would this potentially let you see the 1 over n corrections away from that strict line? Is there some coding that?
No. So what this does is this result allows you to describe the local operators once you've got rid of trace relations.
Right.
So now once you know the space of local operators, you can try to compute the OPE, including 1 over n corrections. But you will be using the same space of a local operator described by this result. So the final part of the Lloyd-Quillen-Segan story allows you to tells you what cyclic cohomology is for a certain A. So let me tell you the answer. So suppose that A is a free commutative algebra on even variables xi and odd variables epsilon j, then a cyclic cohomology bay can be computed as a cohomology of the cochain complex where I take my original algebra with my even variables let me see, did I get a duality mixed up? So I want to make sure I haven't messed up a duality, so I need to. I have variables dual to my commutative variables. So what you should think is this. In some examples, these might correspond to space-time. And these variables saying I can differentiate my operators in the space-time directions. I have my original odd variables, they stay. We introduce some indexing. And I get some you guys, eta I. So it's some big algebra where I have even variables, the same even variables and odd variables like I had before. And I want to introduce extra odd and even variables, where the differential is d eta I is d del xi Sorry, I need to remember the formula. Yeah. So let me change notation. Sorry. Oh, okay. Sorry. All this times t. Okay, so this is a bit complicated. Maybe I could think for a second and simplify it. But are there any questions?
So gamma alpha is also even.
Yes.
How about t?
T is also even. So let's one second. I think I have something slightly wrong. Let me just make sure I don't with the formula for the differential. Oh yeah. Let's leave it for now, and maybe there might be a slight. I'm slightly concerned about the form of this term. So let's leave that for now. So let's look at some examples. So suppose that A is just a polynomial algebra and some even variables, no odd variables. Then cyclic cohomology of A, which is supposed to correspond to certain single trace operators, is generated by del I eta I t, or the differential of eta I is t del I. And this is supposed to correspond to the Lie algebra cohomology of A tensor Lie. So the way the correspondence works is some polynomial in the dells goes to a linear functional, which stands like fxi times a matrix to del I1, del In, f at 0 times trace of the matrix. So like what are the possible invariant things I can have which only have one element of here? It must be a trace on the matrix, and I can just apply any linear operator there. So I differentiate my guy a bunch of times and evaluate at 0. Something with an eta 1 with 1 eta goes to a quadratic functional. For example, if I take some del I times eta I, this gets sent through the functional. I take f g gets sent to f tensor m1, f2 tensor m2 gets sent to, well, I'm going to take the trace of the product of the matrices, m2, and then f1 d f2 0. And it keeps on going like this. So there's a little, like even at this level, there's a little content because things of this form are not always going to be closed under the differential. They will be, there's some, you have to use this relation to build some linear combination of expressions like this, which are closed. I feel this is super unprepared, but is that helping you at all, Surya? Like, is this?
Yeah.
Is it okay, so should I try to do more examples, or should we move on to the kind of witten diagram story we're going to study.
Could you say some words about the example of this that's relevant for the, like how to apply this to?
Yes, yeah. So take the example. When A is a polynomial in 1 even and 2 odd variables. Let me think for a moment. To clarify something in my head. Let me write the complex, the cyclic cohomology complex, slightly differently. Like the kind of small complex. So what we can write it as forms in 3 even variables, one of which, where the forms in this x direction must be supported at a point. So that looks like sorry, it's hard to think at the board. Yeah, so firstly, there's one piece which is going to look like these two guys. If you recall our formula, there were certain even variables associated with them. So we can manipulate the expressions, and we'll introduce 2 new even variables. I'll call that EZ1, EZ2. And then the other piece I'll have spanned by the delta function at x equals 0 and dx times the delta function at x equals 0. So these are like forms which are supported at a point. And the differential is t times the de Rham differential on the z's, t times the de Rham differential on the x, where the x de Rham differential so this expression is like E correct expression for the entire single trace operators.
Should there be a T somewhere in the complex?
Yes. And if you want to write down the things which are closed, over here, for example, we can have any 2 form times this piece, or a closed 1 form times that piece. That will give you a big list of closed things, and those will correspond to the fundamental operators. For example, there would be like F, Ci, dz1, dz2 times dx delta x equals 0. And so on. So with a bit of work, which I think I'm unable to reproduce right at this moment, you can look at this formula and realize that it matches exactly the expressions for the single trace operators we wrote before. Okay, but since we're here, I want to explain a conceptual understanding of this result, which you can then kind of forget about the details. If you want to. So there's a small amount of manipulation in turning this conceptual picture into the standard mode equivalent secant arguments, but it's not hard. So if you look at the closed string field theory for the B model on C3 as fields, one way to write the fields, you can write them as polyvector fields, like we did before, or we can write them as differential forms. So omega star C3 join P with differential D bar plus T thou. So any field, we have a brane drop C inside of C3. So any closed string field which intersects, whose support is like a delta function in this direction, is supported at 0 in this plane, gives rise to a single trace operator. The world-shape picture is I take my disk, I put my single closed field in the middle, and I put my open string fields on the outside. Because I'm assuming that this closed string field is like a little blip at this point on C, it's a local operator at that point. So this is the key thing. And the load equivalent secant theorem is precisely the statement that these are all of the single trace operators.
Are you using the word single trace as a BRST closed operator, or trying to gauge this?
Yeah, good point. I mean to say the BRST cohomology of the single trace operators. So, Bode-Cohen-Secant theorem. Single trace operators is isomorphic. The cohomology of the closed string fields which are supported at a point. Okay, so as you can see, I have trouble remembering some details of how all these manipulations go. But this statement is a statement that everybody can remember and is a true statement with a clear physical meaning. Right? Whenever I have a closed string field, which is like a little blip at this point, I get an operator. These are all of the operators. So if you forget everything else, this is the only thing you should understand. Any other questions?
Can I build multi-trace by just...
Yeah. But this product's that. So probably, this is all at the level of some kind of supersymmetric localization. If you ask, was this true in the physical theory on a D3 brane? It would be, you would realize that there's a gigantic number of single trace operators, so that this result cannot be true in the supergravity approximation. It can only be true at the level of string field theory, because there's just way too many operators on a single D3. But it should be true at the level of string field theory. Okay, any other questions? So should I say a little bit about Witten diagrams? Yeah. So I realized last time that the Witten diagram story is much easier if in the bulk we also have an open string sector. So let's recall to the parallel algebra is the BRST reduction of, these are adjoint valued symplectic bosons. And so we, of course, use these seagulls as usual. This is what we get for C inside of C3. So it's going to be convenient to include a space-filling brane of dimension k/k. This means we get matter fields I, which is in the bifundamental of GLK/K, is GLN. And ij over z, all the indices contracted, and they're both of spin half. This is just a slight generalization. But the important thing to notice is that you can write down all of the gauge invariant operators quite easily. And they come from open string fields as well as closed string fields. Like the same principle, like the single trace operators should be given by little open, single trace closed string operators given by closed string fields, single trace open string operators given by open string fields, which are little delta functions. So, single trace BRST cohomology. Well, we have things like trace ZI1, IN, where the brackets indicates that these are symmetrized. There's other closed string operators. But there's also the open string operators. There's I. These are the ones that are going to be actually easiest for us to describe. So here, we're always contracting all GLN indices. This I1 up to IK, that's I1 takes values 1 or 2. So think about what representation this lives in. This lives in the adjoint of GLK slash K. Because I have the fundamental at one end and the anti-fundamental at the other. It lives in the spin K over 2 of SU to OR, because I have K of these guys of spin half. And it's of dimension K over 2 plus 1, because each of these guys is dimension half, and then I have the I and J also dimension half at the end. So we want to, so we're going to study the holographic dual of these operators, and there'll be open string excitations on the holographic dual. The holographic dual is SL2C with a rank K slash K bundle. Like there's a space filling brane on it corresponding to these open string fields. So we have full string sector, which is Kodaira-Spencer theory. And then the open string, which is holomorphic Chern-Simons for GLK slash K. So what we're going to do is, everything okay? Or what we're going to do is compactify the manifold, put some boundary condition for the open string sector, and then modifications of the boundary condition will be by those operators. So we discussed this last time. Boundary of SL2C bar is a compactification, or the boundary is P1 times P1 with coordinates Z and W. Z is going to be the chiral algebra plane. W will be acted on by SU2R. And we asked that the gauge field of holomorphic Chern-Simons theory should vanish on the boundary. So now we can just study solutions of the equations of motion which satisfy this constraint except at a point on the z. So we can use coordinates n, z, w near the boundary, near, say, C inside of P1, where boundary is n equals 0. And unfortunately, you can't use coordinates where this function z is holomorphic. So there's a Beltrami differential. Which looks like capital N. And n transforms like dw to the half. So n is a section of O minus 1 on the CP1. So n squared looks like dw, so this thing looks like the natural volume form on CP1. Okay, so how would I modify the equations of motion? Like, how would I write down a solution to the equations of motion which does not satisfy the boundary condition? My first guess would be I can define A to be a delta function at z equals 0 times some Lie algebra element. Now this violates the boundary condition because the boundary condition was asked that the gauge field vanish at the boundary, and this does not vanish at the boundary. But this does not satisfy the equations of motion. If z was a holomorphic coordinate, it would be fine. D bar of it would be closed. But because of this Beltrami differential changing the complex structure, this does not satisfy the equations of motion. The failure to satisfy the equations of motion is given by applying this guy to this guy, which gives me the derivative of the delta function. So I have to add on a term, which looks like n squared dw bar over 1 plus squared times 1 over z squared. Right. This fails to satisfy the equation of motion.
So where does the Carroll algebra live?
Sorry, I wasn't clear. So the Carroll algebra lives on the z plane.
On the same.
So we're defining a modification at a point on the Carroll algebra plane.
If we take large n, how do you solve the solution?
The factor of n can be absorbed into a redefinition of the coordinate little n. So it really only appears. The factor, there's only one parameter, which is the string coupling constant. Because SL2C, like the UV, there's a U1W2 plus U2W1 equals n. I can absorb n into a redefinition of the coordinates, but that changes the volume. So the only parameter is the holomorphic volume of the 3 cycle. This is the string coupling constant. Yeah, okay, phew. I did get this correct. So you notice that the leading order term is completely localized. This is my boundary, n equals 0. The leading order term is localized at this point, but once I go beyond this term, it spreads out rapidly. So this is a standard thing in holography. And later we'll be able to relate the value of the subleading term at some other point will be related to the holographic two-point functions.
There's a TA.
Yes, sorry. But before getting there, we should stop in a minute. Let me just, we've listed all of the single trace open string operators. They're just I string of z's j. And if you consider the possible ways to write down field which satisfies the equations of motion except at a point, they are like the same space. So let's look at the next term. So this term, if I remember correctly, corresponds to ij. Well, the next term, I could have a could look like 1 over n. Delta z equals 0. Ta plus corrections. And to see what representation this lives in, we notice that n has a pole at w is infinity. So 1 over n has a 0. So something like this can have two components. Like there's two versions of it, because I can have a equals w over n as well. And you see, the higher the power of n, the more possibilities for w. So the general one is like a equals w to the l over n to the k, delta is equals 0, for l less than or equal to k. So these subleading terms can be written down explicitly. But let's not worry about that for now. Let's just look and see that it matches what we found earlier. So firstly, the SU2 OR symmetry rotates W. So under SU2 OR, this W to the L over NK, that is equal to 0, is in the representation of spin k over 2. And it has dimension, well, it turns out that n has dimension
Spin L over 2.
K over 2, because L runs from 0 to K. So L is an index for a basis of that representation. So K tells me how high I can go up the dimension. So it's a representation of dimension K plus 1. And as a dimension, I kind of Lorentz spin. If I get this right, well, it should have dimension k over 2 plus 1. Yeah, that's right. K over 2 because n has dimension minus a half, plus 1, because the delta function has dimension 1. And of course, under the GLK/K, it's in the adjoint. So if we write down the possible ways of modifying the boundary condition, this is kind of the most general thing except for differentiating with respect to z, and the possible single trace operators, you just see that they're the same set of representations.
Sorry, you said chiral algebra lives on the C plane?
Yes.
And W is the kind of flavors entry that generate SHR?
Yes.
Then I don't understand how that vector corresponds to increasing representation of spin K over 2, not L over 2.
Right, so this is so n is a section of O minus 1. So this whole thing lives in H0 of the CP1 with coefficients in the bundle O of K. Like this is, the value of K specifies what order of pole that this part can have at infinity. And the various representations can be described as functions in CP1 specified order of pole at infinity. So if you want, it's possible to write an explicit formula for the whole thing. But it looks like, I won't write down all the terms. It's not hard, actually. The formula looks like n minus k, delta function z equals 0, times ta, plus a bunch of terms which all involve delta functions and derivatives, and then a non-local term. These terms are all local. And the non-local term looks like n to the k plus 2 Okay. So what you learn from this expression if you think about the 2-point functions for a little bit, so this thing here might correspond to like trace I, Z, 1, J, where power. Yeah. So if we look at this expression, we look at the subleading term, and it has a power of 1 over z to the k plus 2. In this we learn that the 2-point function between two such operators is of order n with k plus 1, z minus k minus 2. And this is correct I look at the 2-point function in this description, I get it by contracting things. So on. Like, how many powers of z are there? There's 1 power of z for everything in the middle, because each guy is a symplectic boson and the OP is 1 over z, and 1 for each thing on the end. That's z to the 1 over z to the k plus 2. How many powers of n? Well, I can label every face by an n, so that's n to the k plus 1. This is the correct count. And the simplest case is this one here. This tells us that the Casmudi central extension, because this guy is the current for the GLK/K symmetry. This tells us that the OBE of 2 currents involves the constant times 1 over z squared, the 2-point function of the currents, and it's proportional to n. It's also correct. And you can work a bit harder and calculate 2 and 3-point functions if you really want to.